When a power supply such as a battery is hooked up to a capacitor, in this case a parallel plate capacitor, then the positive terminal of the battery creates a high electric potential, and the negative terminal creates a low electric potential. And by the way, if we just choose a reference where we set the low electric potential equal to 0, so that the electric potential at the negative terminal of the battery is 0, then the high potential that creates the potential difference would be V high minus V low, but we're setting V low equal to 0, so really there's no difference between delta V and V. So when we write the equation for capacitance, charge is equal to capacitance times potential difference. If we always agree to set the value of the electric potential at the negative terminal of the battery, sort of as a just a standard reference frame, just by convention, if we set that equal to 0, then we can change this to Q equals C V, right? We can ignore the delta and just assume what we mean by V is the voltage, not necessarily the high electric potential. Okay, so the high electric potential removes electrons from the top plate, leaving it positively charged. Ultimately, these electrons are conducted through the connecting wires and transferred to the bottom plate, making it negative. Once the difference in electric potential across the plates matches the difference in potential provided by the battery, electrostatic equilibrium is achieved, and the final maximum electric field between the plates is created. So how much work is done in transferring the charge? As these electrons are moved through the circuit, how much work is done by the battery? Well, work done by electrostatic forces is conservative. So the same amount of work to move the electrons through the external circuit should be exactly the same as if the electrons were moved from the top plate through the gap to the bottom plate. In other words, through this internal electric field. So let's think of it like this. We're going to remove, first of all, the charge on each plate starts out 0. Both plates are neutral. And the very first electron then is transferred from the top plate to the bottom. So that makes the top plate very weakly positively charged and the bottom plate very weakly negatively charged. And then we'll say a very weak electric field develops, signified by just showing one electric field line. Now, the next electron is transferred. Okay, so the top plate becomes a little more positively charged, the bottom plate a little more negatively charged, and the electric field becomes a little bit stronger. Okay, so the electric field is increasing in strength as the amount of number of electrons is transferred, or as the charge on the upper plate increases. So to find the amount of energy stored, we'll say U stands for electrostatic potential energy. We'll say that's equal to the amount of work done to transfer the charge is actually equal to negative the amount of work done, right? And work is the integral of F dot ds. And if we're imagining the work done by moving the electrons through the wiring of the external circuit is the same as the amount of work that would be done by transferring these electrons directly through the electric field, then we can replace F with QE. So here this Q would be the charge of each individual electron. So the potential energy is equal to negative QE dot ds. But negative E dot ds is the same thing as dV, right? So U is equal to the integral of Q dV. Now what's Q? Well, back to our definition for capacitance. Charge is equal to capacitance. We could say delta V, but as we stated earlier in this video, if we choose a frame of reference where the low potential is 0, then we can get rid of the delta sign. So in other words, Q at any instant should be the capacitance at any instant, or I'm sorry, the capacitance multiplied by the voltage at any instant. So I guess when we say Q, that's going to represent the maximum amount of charge on the positively charged plate once electrostatic equilibrium is achieved, whereas lowercase q is some amount of charge anywhere in between the initial neutral value and the maximum value it's going to achieve. And by the way, I guess capital V means the maximum potential difference across the plates that matches the voltage of the battery, and perhaps this is really a lowercase v, and I certainly don't mean velocity by that. Again, I mean just whatever the value of the potential difference is at any instant as the voltage varies from 0 when it's initially uncharged until the capacitor's voltage finally matches that of the battery. Okay, so the potential energy is equal to the integral of capacitance times instantaneous voltage times dV. Capacitance is a constant unless we change the dimensions, right? The capacitance of a parallel plate capacitor is epsilon naught A over D. So assuming we keep the area and the distance between the plates the same, capacitance is a constant. So now we have the integral of V dV as the voltage goes from 0 up to the voltage of the battery. So this becomes U equals capacitance times 1/2 V squared. Or in other words, the potential energy of a capacitor is 1/2 CV squared. Let's check the units on this. Capacitance is in farads, and voltage, of course, is in volts. So what's a farad times a volt squared? Well, a farad is a coulomb per volt. So we cancel one of the V's, and then we're left with coulombs times volts, but a volt is a joule per coulomb. So yeah, we're left with joules when we use this equation. That's satisfying. There's actually 3 forms for the equation for potential energy because we can make substitutions. For example, we can substitute away the C from this equation and replace it with Q over V. So then we would get potential energy is 1/2 times Q over V times V squared, or in other words, 1/2 QV. Likewise, we could have substituted away the V by replacing it with Q over C. So then we'd have U equals 1/2 C times Q over C squared. So one of the C's would cancel out. So we would have, well, anyway, we would have 1/2 C Q squared over C squared. Okay, so now one of the C's cancels out. So we get Q squared over 2C. All right, so let's summarize here. The potential energy stored in a capacitor is either 1/2 CV squared, 1/2 QV, or Q squared over 2C. Now this is kind of interesting, isn't it? As capacitance goes up, what happens to potential energy? Well, this first equation would lead you to believe that it goes up, whereas this third equation would lead you to believe that it goes down. Well, that's kind of a mystery. I'll let you think about that on your own, and we'll solve that mystery in a future video lesson.